the circular motion answer key for the circular motion practice problem set from WebAssign. And we're going to start with this first question about the centripetal acceleration at the equator of the Earth. So what we're given in this particular problem is the radius of the Earth, and that's it. And so we're asked to find the centripetal acceleration. We know from our lab work and reading that centripetal acceleration is equal to the tangential velocity squared divided by the radius of the circular path. So we're given the radius here, right? We're given that r equals 6.371 times 10 to the 6th meters. But we're not given that velocity. And so in order to find the velocity, you got to actually use your brain a little bit. So how fast is that point actually moving? Well, we have a circle that we're moving around. The circle, as the Earth rotates, that circle traverses a total distance of the circumference of the circle, so 2 pi r. And it does that over a time of 1 day. That's obviously not a given piece of information, but you should probably know that the Earth rotates once every day. So that's 1 day, 24 hours. That would be 1,440 minutes and 86,400 seconds. So my velocity is going to be that distance over time, which would be 2 pi r over t. Plugging that into my equation for acceleration, that would be 2 pi r over t squared over r, which would be 4 pi squared r squared over t squared r, or 4 pi r over t squared. And that would give you that centripetal acceleration once you plug these numbers in. So that's this first problem. Boink. Correction, it's not 4 pi r, it's 4 pi squared r. Forgot to carry that squared forward. 4 pi squared r. Okay, for the second problem, 2a, we start with an astronaut orbiting Earth, preparing to dock at a satellite. The satellite is given a circular orbit of 600 kilometers above the Earth's surface. So this piece of information right here is partially telling me the distance to the center of the circle that the satellite's moving through. That's above the Earth's surface, though, so I must also include the radius of the Earth. So the radius of the satellite is going to be equal to the radius of the Earth plus 600 kilometers, which would be 7,000 kilometers, or 7 times 10 to the 6th meters. So that's my r value here. I'm also told that the acceleration at that point is equal to 8.18 meters per second squared. Now, that is the acceleration of free fall at that point. What is the significance of that? Well, the significance of that is that free fall is actually what's keeping the satellite in orbit, right? The force that continues the circular path is gravity, and the acceleration associated with that is the acceleration of free fall at that point. So this acceleration that's given is actually the centripetal acceleration. So I'm given my r, I'm given my a. Last, I just need to solve for that velocity. So I'm doing my centripetal acceleration is equal to v tan squared over r. And v tan would be equal to the square root of a times r. Plug in your numbers, chug out an answer. All done. The second part of this question is evaluating the time required to complete one full orbit around the Earth. This time for one full revolution is also referred to as the period. And period, as you read, is denoted with a capital T, period. And that's the equivalent of the time taken for one full revolution. So in order to answer this part of the question, I need to know both the velocity, which I solved for previously, and I need to know the total distance that I'm covering, right? So my v is going to be my d over t. Time is going to be distance over velocity. That distance is, again, the circumference of the circle. So that'd be 2 pi r of the satellite divided by the velocity, which is the square root of ar. Okay, so again, solve that out with your numbers that you're given, and you should have the solution. For this next question, this is purely conceptual. So it asks, which of the following particles, if any, have an acceleration? A particle moving in a straight line with constant speed. That's a no. And the reason it's a no is Newton's first law, right? An object moving with constant velocity has no unbalanced outside force, and therefore no acceleration. So that's not correct. But the second one is correct. That a particle moving around a curve with constant speed is accelerating. The reason for this being acceleration is proportional to change in velocity, and velocity is a vector. So direction matters. Right? Velocity factors into direction. So curved path would mean that we are changing direction. Which would in turn mean we are changing velocity, which would in turn mean we have a non-zero acceleration. Okay, so this next problem has a figure given, and that figure represents the total acceleration, or what we might call the resultant acceleration or the net acceleration, right? And that net acceleration has two components, right? If you look at the image, it's not directed towards the center. It's also not directed tangent to the circle. So what this means is there will be a centripetal acceleration, some component directed towards the center of the circle, and some tangential acceleration here. We're given the acceleration vector as well as the angle. So we can break that down into its components. One component directed towards the center will be the centripetal acceleration, and the tangential acceleration will be the component directed tangent to the circle. So we could say AC, or the radial acceleration as they refer to it here, is going to be A times cosine theta. And that's going to be my answer to 4A. Okay. At that point, once I know that AC, that's equal to the instantaneous tangential velocity squared over r. So to solve for the speed of the particle there, the speed of the particle there would be the square root of AC times r. And then lastly, The tangential acceleration would be the sine of that angle. So that would be a sine theta. And that's it. Pretty straightforward, but you have three separate sort of conceptual sections here. The last question on this problem set is another conceptual question. So it's not really asking you to quantify an answer. It's asking you to respond with explanation. So the question says, can a particle moving with an instantaneous speed of 6 meters per second on a path with radius of curvature 3 meters have an acceleration of magnitude 22 meters per second? So it's saying, if I'm moving around some sort of a curve, it doesn't say that that has a constant radius, right? It just says that it is moving along a curved path, and at that moment, it has a radius of 3. So that's 3 meters. This is 6 meters per second. Can the acceleration be 22 meters per second? Well, in this case, if it's moving along a curved path of that radius, the absolute minimum acceleration would be the centripetal acceleration. That would be the smallest value it could be in order to be moving in that circle. So I would take that and say that's equal to v tan squared over r, right? And solve that out. In this case, that would be equal to 6 squared over 3, or 12 meters per second squared. Now, that would be the smallest acceleration. Could it be bigger than that? Yes, it could. This would be the minimum acceleration. But if the particle also experiences a tangential acceleration, then the total acceleration, the resultant, right, can be greater than, sorry, my dog's whining in the background, the centripetal acceleration. So centripetal acceleration would be the smallest value it could be in order to maintain that curved path. But if it's also speeding up translationally, then it could have both a centripetal and translational or tangential acceleration, the vector sum of which could be as large as it needs to be. In this case, it could be 22 meters per second squared. So the answer to this first part is yes. For the second part, can it have somebody's at the door. Can it have an acceleration of magnitude 11 meters per second squared? No. Because the minimum centripetal acceleration is 12 meters per second squared. If the acceleration was less than that value, then it would not be on this curved path. So in this case, the answer is no. The minimum acceleration it can have would be 12 meters per second squared in order to be on in the given constraints that they've assigned with this problem. And that's it.